So far, we focused only on the things that make up matter on the atomic level. What makes an atom, how atoms form ions and molecules, and how we think about particles in solution. A lot of how we can apply chemistry and how we learn about chemistry is how we can actually observe the changes in chemical reactions. When we describe chemical reactions, we have a systematic way of describing that reaction, called the chemical equation. A chemical equation shows the things going into a chemical reaction, the reactants, and what they can become if they react, the products. We know from earlier on that matter is conserved. Whatever goes into a reaction, and only what goes into a reaction, needs also be what comes out as products. This is true down to the atomic level. The same number of each type of atom needs to show up as reactants as we see as products. So in the example shown, we need to have just as many carbons indicated by the black spheres in the reactant and product. Same thing with oxygen and same thing with hydrogen. If a reaction is written in such a way that the number of atoms of each element is the same in the reactants as it is in the products, the chemical equation and the reaction it describes are said to be balanced. Let's be clear, reactions are always balanced. The chemical equations that we use to express them are most representative when they are also balanced. If the chemical equation is balanced, it allows for us to see the ratio of molecules or moles within the reaction. For example, here we see that 2 different water molecules are formed from every methane molecule, or 2 moles of water are produced for every mole of methane, which we can actually use as a conversion factor, one of the major things that I want you to see in this chapter. Here we see a chemical equation for one of the most significant reactions of our time, the conversion of atmospheric nitrogen to ammonia, which can be used as fertilizer. This reaction, catalyzed in the Haber-Bosch process, no relation, accounts for at least 1% of global energy demand and is likely responsible through food for at least 50% of the nitrogen in your body. But the reaction isn't balanced unless we put coefficients, numbers, in front of each molecule to represent the right ratio of molecules. It's important to remember that mass is always conserved and that atoms never change in chemical reactions. Nuclear reactions do follow different rules. Together, these imply that the number of moles of atoms will never change. It's also important to remember that each molecule represents a discrete unit. We can't change the subscripts on any molecule. We can only change the number before, the coefficients. So the NH3 has to come as a complete package, and the H2 has to come as a complete package. When I balance a reaction, I'm always going to start by assuming that I know the coefficient for the most complicated component of the reaction. Here that's ammonia, NH3, because it has both types of elements. I generally assume a value of 1. You have to start someplace, and 1's a good place to assume because it makes your math easier. From this initial assumption, I can multiply the coefficient by the subscript for each atom to figure out the total number of atoms on each side. The coefficient 1 that I assumed is multiplied by nitrogen's subscript of 1 to tell us that we have 1 nitrogen atom in the product. The same coefficient applies to the 3 hydrogens in ammonia, indicating that we have 3 total hydrogens in the product. As long as this molecule is the only source of these atoms on this side of the reaction, we know that the other side of the reaction will also need to have the same total number of each atom, 1 nitrogen and 3 hydrogens. We also know what the subscripts are for nitrogen gas and for hydrogen gas, our only sources of each atom. Because we know the total number of atoms and the subscripts, we can divide atoms by subscripts for the coefficients of each molecule. For nitrogen, we get 1 divided by 2 equals 1/2, which becomes the coefficient for nitrogen in the equation. Similarly, 3 hydrogens divided by the 2 that we get from each H2 molecule gives us 3/2, which shows up as the coefficient for hydrogen in the equation as well. While this reaction is technically balanced and will work just fine for everything we need to do with it, chemists have collectively decided that they don't want to deal with fractions in balanced chemical equations. For this reason, we will generally multiply our coefficients to become whole numbers if we have fractions in our solution. The lowest whole number ratio is considered the correct expression of a chemical equation. Here, if we multiply every coefficient by 2, every number will become whole. The correct expression for this chemical equation then would have 1 nitrogen molecule for every 3 hydrogen molecules and 2 ammonia molecules. While we wrote out the coefficient here for nitrogen, it's pretty common to assume that and omit coefficients of 1. So this is probably how we'd actually see the equation if it was written out. Most reactions that transform molecular compounds require this type of balancing by individual atoms. The reaction shown is the combustion of ethanol. This example is a little bit more complicated because oxygen shows up in every molecule. But we can use the same strategy to balance the equation. We start by assuming the most complicated molecule, in this case ethanol, has a coefficient of 1. This allows us to know how many carbons, hydrogens, and oxygens are added to the reactant side by ethanol. In this case, 2 carbons, 6 hydrogens, and 1 oxygen. It's important to remember that molecular oxygen is also a reactant, but we don't know the amount that we'll need to balance, and we don't know the coefficient yet. Since there's only one source of carbon in the products though, and we know that 2 carbons from the reactant need to show up in the product, we can figure out that the coefficient for carbon dioxide would be 2 divided by 1, or 2 carbons. Carbon dioxide needs to have 2 molecules to deliver those 2 carbons. But whatever the coefficient is for carbon in carbon dioxide, it's also the same coefficient for the 2 oxygens in carbon dioxide. So you'd have 2 times the subscript of 2 for oxygens to give us 4 total oxygens delivered by carbon dioxide. We can solve for the coefficient of water using hydrogen in the same way. See if you can figure out that part, the coefficient for water, and then use it to figure out the amount of oxygen from water on your own. Since there are 6 hydrogens in the reactant, we know that there are 6 hydrogens in the product that must come from water as well. Each water delivers 2 hydrogens, so we take 6 divided by 2 and know that we need a coefficient of 3. And just as before, that same coefficient applies to the oxygen of water as well as the hydrogen. So we know that water delivers 3 oxygens. 3 times the 1 oxygen per water gives us 3 oxygens. To balance the oxygens between reactants and products, we now need to consider all the sources of oxygen together. In the product, we have 4 oxygens from the carbon dioxide and 3 from the waters for a total of 7 oxygens. Since the reactants need to match, we know that there will also be 7 oxygens. Since we know only one of these is from the ethanol, the other 6 need to be from oxygen, which means that oxygen must have a coefficient of 3. Since our coefficients are all whole numbers in this case, the coefficients are correct as written, and we've successfully balanced this equation. Some of the most readily observed reactions are precipitation reactions, which often occur when soluble salts combine and yield an insoluble component, the precipitate. There are a few new things to think about in this equation. First, since phase changes are often readily observable in the reaction, the chemical equation includes information about the phase of a reaction as a subscript, G for gas, L for liquid, S for solid, or AQ for aqueous, which means a solution dissolved in water. So we might describe the equation in words by saying that aqueous sodium chloride, the reactant on the left, combines with the next reactant, aqueous silver nitrate, to yield aqueous sodium nitrate and solid silver chloride precipitate. Even though we talk about sodium nitrate as a new compound, it's actually still dispersed as individual sodium plus and nitrate minus ions. Only silver chloride is actually changed, because the ions remain dissolved if they're not precipitating. We sometimes will write out a complete ionic equation to make this more clear. In a complete ionic equation, every aqueous salt is listed as its individual ionic components. The precipitant is the only thing that will actually change and is written all together as a solid. In this form, it's more clear that the sodium plus ion that was in solution stays in solution, as does the nitrate. The complete ionic equation has several components that aren't participating. If we only show what is actually changing, we get what we call a net ionic equation. Here, the silver and chloride that start out dissolved are shown to participate by precipitating. You couldn't perform this reaction as written, this net ionic reaction. You need the nitrate to get the silver plus into solution, and you need the sodium plus to get the chloride into solution. But a net ionic equation makes clear what ions are actually reacting and which ions are just watching, but not participating. We call the ions that are present, but not reacting, like sodium and nitrate, spectators, because they're only watching. Since precipitation reactions involve ions combining without changing, we can simplify our calculations for balancing the reaction by balancing ions all together at once. For example, we can think about balancing sulfates, SO4 - 2, without balancing individual oxygens or sulfurs. Start by assuming one sodium sulfate formula unit and see if you can balance this equation in ions. Remember that a subscript outside of parentheses, like the 2 outside of nitrate, applies to the whole ion, while a subscript without a parentheses, like the 4 after sulfate's oxygen, applies only to the preceding atom. If we know there is one sodium sulfate, but that each supplies 2 sodiums, we know that there are also 2 sodiums in the product. In the product, each sodium nitrate delivers only 1 sodium, which means that we need 2 sodium nitrates. This applies to both the sodium and the nitrate, so we can figure out how many nitrates we have in the product by multiplying the coefficient of 2 by the subscript of 1 for a total of 2 nitrates. Notice that there is no indicator on the NO3 that all are one polyatomic ion and can be treated as such. That's why I had you memorize common ions back in chapter 3. If you don't get those down, this becomes much harder. If you don't remember those, that's a good place to review. The remainder of the problem can be solved in any order, but I chose to fill in the remaining subscripts all at once. Then solve for the magnesium nitrate coefficient by matching nitrate from the product with the reactant side and dividing by the subscript. The magnesium in the reaction is just the product of coefficient and substrate and is matched on the product side. Solving for the remaining coefficient by dividing 1 by 1 tells us that there is only 1 sulfate in the product, which matches with the reactant. So we know we did it right. Woot! There are many types of reactions, but some of the most readily observed reactions fall into a few simple categories. Precipitation, shown in the top left, result in a phase change, and generally are from double displacement reactions. 2 soluble salts combine to precipitate out a new, less soluble salt. Predicting these reactions involves having a general sense of what makes something soluble, which is next up for us. Redox reactions, short for reduction-oxidation, often also involve a phase change, either precipitating something out of solution or generating a gas. Redox reactions at this level are often one metal oxidizing to enter solution and replacing another metal in a salt. But redox reactions are widely varied. A special case is combustion, combining a carbon-based molecule with oxygen to make carbon dioxide and water. Incidentally, the combined reactions of your central metabolism, many of which are redox reactions, sum up to combustion reactions. You really do burn calories. Acid-base reactions in the top right are the final category of easily observable reactions, with the famous baking soda volcano as a notable example. However, most of the time our acid-base reactions are not quite as obvious, and we observe them instead by changes in the concentration of H+, or hydronium, which we can see with indicators or measure with specialized probes. Precipitations, our first category of reactions, occur when we combine ionic compounds to make one combination of ions that are less soluble in water. This generally occurs when the ions have either very strong attractions between themselves or very weak interactions with a solvent like water, because like dissolves like. Water can't replace those strong ionic interactions, and it would rather interact with itself than have weak interactions with something else. However, ions with reasonably similar interactions with themselves as with water can readily dissolve. Since water is our most common solvent, we should know some general rules for water. First, group 1 metals and ammonium are always soluble without exception. This makes sense because a +1 charge on the metals can easily interact with water, and ammonium can actually share its hydrogens with water in addition to having a +1 charge. -1 charged oxyanions also tend to be soluble, as the charge is dispersed over several oxygens and can be decreased by water partially sharing hydrogens with them. This makes their interactions very similar to the interactions water has. Nitrate, acetate, bicarbonate, and chlorite are all examples of -1 charged oxyanions that are considered always soluble. Halides in general are also soluble due to their -1 charge and the ability to interact with the hydrogens of water, but they are less similar to water and they can still be precipitated out by late metal salts, particularly silver, dimercury, and lead-2 salts, which are all particularly insoluble. Fluorides are also an exception. They are less soluble because they form such strong bonds with so many metals. Sulfates are generally soluble because they disperse their charge to multiple oxygens, just like other oxyanions, and they can also share hydrogens with water. But they do have a -2 charge, so they can't dissolve silver, dimercury, or lead-2, just like with halides. And they also can't dissolve with any particularly insoluble metals or group 2 metals in general. Hydroxide can form very strong bonds with many metals and are generally not soluble except for the group 1 metals, which we already said are always soluble, and also barium +2, so barium hydroxide is soluble. So if we want to predict a precipitation reaction, we'll often have two salts, one with a group 1 metal or ammonium and a less soluble anion, and the other with a less soluble cation and an oxyanion. Since nitrates are always soluble, but silver salts rarely are, silver nitrate is commonly used as a precipitate for most anions. Acid-base reactions are another class of reactions. Acid-base reactions in the most simple definition, first given by savant Arrhenius, either release H+ ions into solution or hydroxide into solution. Combining Arrhenius acids and bases would make water. This is the most limiting definition of acids and bases, but since Arrhenius developed this idea of ions in the first place, we'll give him a pass. Bronsted-Lowry acids and bases are named after two chemists who independently generalized Arrhenius's work to be an exchange of hydrogens, H+, which widens the selection of bases, but also gives a useful conception of the relationship between acid and base conjugate pairs that's essential to our understanding of acid-base systems. We'll talk about that more in just a little bit. G.N. Lewis, the Lewis dot structure guy who was nominated for the Nobel Prize 41 times but never received it, he came up with an even more general definition the same year that Bronsted and Lowry extended Arrhenius's definition. Lewis's definition fully encompasses the Bronsted-Lowry definition and also the Arrhenius definition, and it allows us to consider a lot of catalysts that aren't based on H+, and most of the reactivity in organic chemistry. Even though the Lewis definition is more powerful, the Bronsted-Lowry definition makes it easier to see relationships between acids and bases, and gets us far more outside of organic chemistry. We'll introduce Arrhenius and Bronsted-Lowry definitions here, with only this teaser that if you work hard to understand Lewis acids and bases in second semester with Vanderwood, organic chemistry will be a lot easier. Arrhenius definitions give us easy access to think about our simplest acid-base reactions, neutralizations. Since acids supply H+ and bases supply hydroxide, combining simply leads to water. The ratio of reactants always needs to be 1:1 to form water. This makes it easy for us to use neutralization for measurements. Before neutralization with a base, an acid solution will have extra H+ and has a very low pH, which is easy to measure. When the amount of acid has been matched with a known amount of base, the solution becomes closer to neutral, but quickly increases to a basic pH with any excess base is added because you have a lot of hydroxide and very little H+, also easy to measure. The reaction is shown as a net ionic equation, but the ions would never actually come by themselves, so there would always be spectator ions that increase the salt concentration in the reaction as well. Arrhenius acids and bases are most useful when we talk about strong acids, compounds that will completely separate to a spectator and H+, and strong bases that will completely separate into a spectator and hydroxide. There are relatively few of these compounds, and you should be able to recognize them when they appear. Strong acids include all hydrogen halides except for hydrogen fluoride. Practically that means hydrogen chloride, hydrogen bromide, and hydrogen iodide, since there isn't much astatine in the world and tennessine exists for like milliseconds at a time and only was discovered in 2010. The remaining acids are fully protonated. That is, they have all the hydrogens to balance a negative charge, and they're acids of polyatomic ion salts. An easy way to remember which polyatomic ion salts they are is that they're the most oxidized, so having the most oxygens possible, of the most electronegative atoms other than oxygen and fluorine. So we have nitrogen, phosphorus, sulfur, and chlorine. Or you could just remember the individual acids. Strong bases are even easier. They are the soluble hydroxides, group 1 metals, and barium hydroxide. I also have included alkali metal hydrides on the list, although not strictly an Arrhenius base, because when the unstable hydride anion reacts with H+, it boils off as hydrogen gas, and so typically can deliver an equivalent amount of hydroxide base in water. It pulls off an H+ and leaves behind hydroxide. Bronsted-Lowry offers a subtle yet valuable change from the Arrhenius definitions of acids and bases. Arrhenius would have defined an acid, here HA, such that it needed to release H+ into water, or, as we'll eventually learn is the case, convert a water molecule to a hydronium ion. Since H+ never actually exists on its own, it's always stabilized by the solvent. All Bronsted and Lowry really did was state that we didn't need to consider water as the only recipient of H+, or protons. Instead, we could think of a base, indicated here by B, as anything that could receive those acidic protons, whether as water, hydroxide, or anything else. This is valuable as it defines acids and bases relative to each other in a reaction, but also because it allows us to think of these reactions as reversible, which they often are. Because after an acid gives a proton to the base, indicated by the H+ going from A to B, the acid becomes able to receive a proton. It is its own conjugate base. And the base becomes able to give a proton. It is its own conjugate acid. For weak acids, like those that occur biologically, the acids and conjugate bases are always being interconverted, which makes this conception indispensable for biology. Precipitation reactions were about ions recombining. Acid-base reactions were about transferring H+, or protons. Oxidation and reduction reactions transfer electrons from one atom to another. Redox reactions are often energy-producing reactions and account for the majority of energy production in our cells. Just like acid-base reactions must always have a donor and a recipient, an acid and a base, redox reactions have both a donor of electrons and a recipient. The donor of electrons loses its electrons and becomes oxidized, and the recipient of electrons gains electrons and becomes reduced. Of course, we need to be able to tell where those electrons are, which we do by assigning oxidation states. Our baseline for assigning oxidation states is the elements. Anything in its elemental state is considered to have an oxidation state of 0. Metals and other monoatomic ions have oxidation states equal to their charge. So an iron 2 with a +2 charge has a +2 oxidation state. A chloride, which has a -1 charge, has a -1 oxidation state. If an atom is part of a polyatomic ion or part of a molecule, then all of the electrons in every bond need to be considered as part of the more electronegative atom in that bond. And we figure out the oxidation state for each atom by subtracting the electrons that are actually considered on that atom from the number of valence electrons normally brought from that atom, in the same way that we have done formal charges. We'll do a few examples in a second. We can always check our work in this type of problem because the oxidation states of every atom in an ion or molecule will add to the charge of the ion or molecule. Let's work through a few examples, starting with the perchlorate ion. Since none of the atoms are elemental or monoatomic, we need to consider each atom by considering the electrons that each atom has according to our accounting system compared to its normal valence. In our accounting system, all of the electrons go to the more electronegative atom in a bond. So since the oxygen is more electronegative than chlorine, the oxygen will be considered to have all the electrons in each of its bonds to chlorine. Each oxygen will have 6 valence electrons normally, but now it's considered to have its full octet since all of its bonds go to it. In 3 of the cases where we have double bonds, we get 4 electrons from the 2 lone pairs and 4 from the electrons in the double bond, Or in the other case, with the negatively charged oxygen in the top right of the molecule, we get 6 electrons from the 3 lone pairs and 2 from the single bond. In either case, the 6 electrons it should normally have from its valence have the 8 electrons that it actually has according to our accounting system subtracted from them to give a -2 charge on every oxygen. So every one of the oxygens in this case has an oxidation state of -2. An oxidation state of -2 is really common for oxygen. Oxygen is more electronegative than everything but fluorine, so it will almost always have a -2 oxidation state unless it's bound to itself or fluorine. Again, in this molecule, the chlorine isn't assigned any electrons of its own, since in every case it has all of its electrons bound to oxygen, which is more electronegative. So we take the 7 valence electrons it normally has and subtract the 0 it has by our accounting system to find a +7 oxidation state. Notice that 4 times the -2 oxidation state, which accounts for all of the oxygens, plus the +7 oxidation state of the chlorine would equal -1, which is the -1 charge overall on the ion. So we know that we did the calculation correctly. The next example is oxygen, O2. Since oxygen is in its elemental state, it has an oxidation state of 0. Remember that there are 7 elements whose elemental state is diatomic. Ozone, O3, is not diatomic oxygen. It's still only oxygens, but it's not considered its elemental state. The central oxygen actually has a +2 charge, and the outside oxygens are -1. See if you can figure out the oxidation states for the 4 remaining examples one by one, and we'll go over them one by one. The first example is manganese. Manganese, or any other atom, is elemental if no charge is indicated, and its charge and oxidation state would both be 0, which is the case here. In this chloride example, the oxygens get all the electrons from the chlorine, oxygen bonds again, because they're more electronegative than chlorine. As before, we take oxygen's normal count of 6 valence electrons and subtract the 8 electrons assigned to it, so each oxygen would get -2 for its oxidation state. The chlorine doesn't get any of the electrons to the bonds, but it does have 4 electrons on lone pairs. Subtract the 4 electrons from the 7 electrons we'd expect from chlorine, and we have a +3 oxidation state for chlorine. The chlorine +3 oxidation state plus the 2 oxygen -2 oxidation states give us a total of -1 for the ion, which checks out. Hooray us! Now we have an example with just 1 oxygen with a -2 oxidation state. The chlorine has 6 electrons in lone pairs, but it normally should have a valence of 7. 7 minus 1 gives us a +1 oxidation state for the chlorine, and if we take the +1 oxidation for the chlorine minus the 2 for the oxygen, it gives us -1 for the whole ion. So again, it checks out. Finally, we have the permanganate ion. We know that oxygen is more electronegative than manganese. Manganese is a metal and oxygen is a nonmetal. So every oxygen will be -2. We probably don't know manganese's valence since it's a transition metal. It's a little bit harder to figure out. An easier way to figure out manganese's charge is to figure out what needs to be added to the sum of all the oxygen -2 oxidation states to give the ion charge of -1 as indicated. Turns out that the manganese needs to be +7 to balance out the total of -8 from the 4 oxygens and leave a -1 charge of the ion. So in this case, manganese has a charge of +7. We sometimes talk about whole molecules as being particularly useful at either oxidizing something else, which means that it will need to be reduced in the process, or reducing something else, meaning it will be oxidized in the process. Something that oxidizes another compound is called an oxidizing agent or an oxidant, while something that reduces something else is called a reducing agent or a reductant. Just like a professional agent for a sports player doesn't get hired oneself, but gets someone else hired instead, an oxidizing agent isn't oxidized, it oxidizes something else. And a reducing agent isn't reduced, it reduces something else. If we look at the example shown here of lactic acid being converted to pyruvic acid by NAD+, which is a biological process that occurs in your liver as part of the Cori cycle, we can see that one carbon changes oxidation state between the two molecules. An increase in the number of bonds to oxygen is one of the most common forms of oxidation. Since oxygen is more electronegative than most things, any increase in the number of bonds to oxygen will decrease the number of electrons available to the other atom, resulting in a higher oxidation state. See if you can identify the oxidation states for each of the carbons that are indicated with the red box. If you need a hint, bonds between the same atom will have one electron assigned to each atom. So if you have a carbon-carbon bond, each carbon will get one of those electrons. The carbon on the left has no lone pairs, so its only electrons will be from bonds. The bond to oxygen will have all the electrons assigned to oxygen, while the bond to hydrogen will have all the electrons assigned to carbon, since carbon is more electronegative. That gives us 2 electrons so far. There are 2 bonds to carbon, and we get 1 out of the 2 electrons in each bond from each, for a total of 2 more electrons from the bonds to carbon and 4 electrons from all of the bonds, 2 from hydrogen, 1 from each carbon. Since that is equal to carbon's normal valence of 4, the carbon has an oxidation state of 0. On the right, for the same carbon, we have replaced a bond to hydrogen with a bond to oxygen. So we'll only have the 2 electrons from the bonds between carbons available to the carbon indicated. The normal valence of 4 for carbon minus the 2 electrons carbon actually has from each of its carbon-carbon single bonds gives us an oxidation state of +2. If we ever get confused about which direction to go with our calculations, it can be helpful to remember that something bound to more oxygens will always be more positive. So in this example, the carbon indicated is being oxidized, which makes the NAD+ an oxidizing agent. That also means the NAD+ is being reduced, and the lactic acid is a reducing agent in this reaction. Many biological redox reactions are reversible. They can go in forward or reverse directions. That means the pyruvic acid on the right can function as an oxidizing agent, and the NADH can function as a reducing agent. This is the process of anaerobic fermentation that allows me to run more than 10 feet and still produce energy in my cells. The next example is an example from organic chemistry. The water on the left and the sodium hydroxide on the right facilitate an acid-base reaction alongside the redox that stabilizes the product. So the actual redox is happening in the other pieces. See if we can identify which of the other 2 reactants, the sodium borohydride NaBH4, or the acetone C3H6O, is the reducing agent and which is the oxidizing agent. Of course, you can absolutely calculate the oxidation state of each atom, but you may also judge based on the relative number of bonds to oxygen as a shortcut. The acetone reactant becomes isopropanol as a product, and the only carbon changing is the center carbon. It has 2 bonds to oxygen on the left and only 1 on the right, meaning that the acetone is more oxidized in the reactants than the isopropanol is in the product. Since acetone is being reduced, it must be oxidizing something else. It is the oxidizing agent. That means that sodium borohydride, NaBH4, is the reducing agent. The calculation for sodium borohydride atoms isn't as clear since the Lewis structure isn't shown, but all the hydrogens are more electronegative than boron and are around the boron. So each hydrogen will have a -1 charge and boron has a +3 charge. When we move that hydrogen with a -1 charge on boron to a carbon, it becomes +1 because the carbon is more electronegative than hydrogen, which means that the hydrogen was oxidized. For many redox reactions, it's convenient to talk about the behavior of oxidants and reductants separately. It can make explicit which particles are being oxidized or reduced, but it also makes calculations of things like energy of reactions and balances between reactants and products, which are both common later on in chemistry, a lot easier to perform, and it allows us to have standard references for those. To write an equation as what we'd call a half-cell reaction, we must consider each species that's changing in oxidation state independently. In this single displacement reaction, zinc is being oxidized from its metallic state with an oxidation number of 0 and becoming zinc +2 in an aqueous solution. We know that zinc needs to lose 2 electrons to make these changes, so we put 2 electrons on the product side along with zinc plus 2. We also can see that hydrogen is changing. It starts out with a positive 1 oxidation state since it's bound to a much more electronegative chlorine, but it ends up with an oxidation number of 0 in its elemental form of H2. For this half cell, we say that H plus needs to react with an electron to form 1/2 of a hydrogen gas molecule. Half cell reactions are often written so that H plus comes off as just 1, or other atoms being oxidized or reduced come off as single units as well, without regard to fractional coefficients in other parts of the equation. We could write the same equation in the form on the bottom, which is also a correct expression of that half cell, but typically only the H plus plus E instead of the 2H plus plus 2E minus is listed as a standard value, so it's a lot easier to look up the middle reaction. The number of times a half cell needs to happen to balance the equation would be different between the middle and bottom equations, which we'll eventually need to take into consideration when we do that type of calculation. And you'll talk a lot more about this in an electrochemistry unit with Vanderwood next semester. Half cell reactions never occur on their own. They must always be coupled with another half cell, so the electrons actually have some place to go. If we didn't have two of the middle equations, 2 H pluses plus 2 E minuses, happening at the same time as the top equation where zinc becomes oxidized, we just have electrons floating around, which doesn't happen at least until second semester organic. Many redox reactions occur in water, and water often will be a convenient source of oxides and protons, O-2 and H+. As these often don't change oxidation state as they bind other atoms, water and acidic protons are frequent spectators in redox reactions. The seeming complexity of these reactions is drastically reduced in the half cells, which ignore the spectators and focus only on the change in oxidation state between the reactants and products. Let's walk through this example. If we're taking gold plus and oxidizing to gold 3 plus with the dichromate, the chromium oxidation state becomes +3, but the chromium also loses oxygens as ligands to water. This could make the reaction confusing, but it doesn't have to if we make two half cells. The first half cell is easy. We have the same number of gold atoms on each side, the left and the right, and we only need electrons to balance it. We can complete this right away since we know that we need 2 electrons to make up the difference in charge between +1 and +3. The other side is a little bit more difficult, but we can at least start with the easy things. Here we can balance the 2 chromium ions on the left by making 2 chromium +3s on the right. We use water to balance the oxygens. Here 7 waters to balance the 7 oxygens. On both sides, oxygen has -2 oxidation state. It's still just a spectator in this redox reaction. Similarly, we balance all the hydrogens with H+, which means we need 14 protons as reactants. This sounds obscene, but protons are constantly being moved around in water. Transits of protons can happen actually faster than most other reactions. This still hasn't changed that we need to balance those electrons. We can do this by figuring out the chromium oxidation state in dichromate, but we can also just use charge. We have a charge of +12 overall on the left, from the +14 with the hydrogens and the -2 with the dichromate. We have a +6 on the right from the 2 chromium +3 ions. That gives us a difference of 8 electrons that need to be added to the reactants. Dichromate has 2 chromium ions that each have a +7 charge, so that actually matches up pretty readily. Since the gold half cell only accounts for 2 electrons at a time, we need to multiply this half cell by 4 so that the electrons balance. Since that cancels out the 8 electrons from the other half cell, I can just add the components of the other half cell to get the overall balanced equation. Because the balance of electrons isn't always apparent in the complete reaction, balancing a reaction by half cell reactions is a much easier way of tracking the electrons to make sure the reaction will actually balance. All we need to do is follow these steps. First, write the half cells, balance the metals, then balance oxygen, balance hydrogen, and finally balance the electrons. Many of the redox reactions we deal with in general chemistry are based on metals. It's worth noting that all fossil fuel energy and all energy from aerobic respiration is from redox reactions as well, the oxidation of carbon. When carbon-containing molecules are oxidized by oxygen, whether altogether when we burn something or a little bit at a time within an organism, the net reaction is combustion. In combustion, carbons get oxidized to carbon dioxide, while oxygen is reduced to water. Carbon-containing molecules are therefore the reducing agents, while oxygen, big surprise, is the oxidizing agent. Again, when you are doing this in little pieces within your cell, redox reactions are still at play. In fact, in your cells, most of the oxidation of carbon is clearly separated into beta oxidation of fatty acids and the citric acid cycle, while almost all of the reduction of oxygen to water occurs in the electron transport chain, perhaps making these roles even more clear in biological systems.